Good morning. Here's the joke of the day. CSI. Cesium CS. Okay, what's the plan? Well, as you know already, this is how it's going to be for the rest of the year, unfortunately. It's not the way I want to do it. It's not why I got into teaching, but this is the way it is. Today, we'll be going over artificial transmutation, which is not that complicated. Tomorrow, we'll look at nuclear reactions, and that might drip over into Wednesday. But on Wednesday, the plan is to go over risks and benefits of nuclear energy, and 5.7 and 5.8 review or drip over. That's Thursday and Friday, and then the test is going to be due on Monday. Nuclear test is going to be due. Okay. As far as the rest of the year goes, you know that this is what the format is going to be. I'm looking at the number of views. Typically, we're getting fewer than half of the people looking at it, which is up to you. If you can get it another way, it's great. The only problem with that is if you are doing some heavy borrowing from other people, there's no way that I can tell, really, except the lab that you would hand in and just copy it from somebody else. But I can't stop you from doing that. The only issue is when we get to the final, it's not going to work out for you. Because if you're not learning this, if you're just getting this from other people, then when it comes to the final, you're going to get hit hard. We do have to have a final in here. It's going to be probably the second week of June. And I'm going to make 3 or 4 different finals. So you're not going to be able to collaborate with anybody because you're not going to have enough time to figure it out. The final is typically takes about an hour and a half. I'm probably going to give you maybe 4 hours, 3.5 maybe. So there'll be plenty of time to finish it, maybe even 3 hours. Plenty of time to finish it, and then you'll have to submit it within that time, and if you don't, then there'll be penalties that go with that. Okay? So I don't want to scare anybody, but you know, you've got to learn this. And I'm having these Google Meets, and you know, I'm getting 6 people. It's the same people each time. But if you're comfortable doing it this way, grades are due this morning. I finished them yesterday. And for the most part, everyone went up, which makes sense because you're looking up all the answers. Again, just be careful with that. Okay, we're going to recap half-life with one question, and then we'll go over artificial transmutation. Homework, I will tell you, is going to be a couple of half-life questions, and then the odds on an artificial transmutation sheet. And I'll post both of those. So let's recap with some half-life. I want you to do number 1 and 2 for homework tonight. So let's do number 3. Get this back up to number 3. If 20 grams of radioactive isotope are present at 1 p.m., 5 grams remain at 2 p.m., what is the half-life? Okay, so I'm going to go ahead and draw my sample here, and it says it starts at 20 grams. Well, half-life, remember, is the time it takes for 1/2 of the sample's atoms to decay into different elements' atoms. So it doesn't tell you what the isotope is, and it doesn't really matter in this case. So when we go from a sample of 20 grams to 10 grams, it's going to take half the time, right? Well, I shouldn't say it like that. It's the half-life. It takes a half-life for that to happen. It's going to take another half-life for us to go to 5 grams. So this is our end point here. 5 grams, started with 20. Half of 20 is 10, half of 10 is 5. And this takes 1 hour. So I'm starting at 1 p.m. and ending at 2 p.m. So if the span is an hour, just divide it by 2 because there are 2 half-lives. So each half-life is going to be 30 minutes. That's a total of 1 hour. Okay? So my answer here is 30 minutes. All right, so that's kind of the same idea. Get out of that. We're going to learn about artificial transmutation today. Let's go into our notes. So far in this unit, which I looked at last year's, it was only 5 days. This year we're spending about 2 weeks, so there's plenty of time for you to absorb this information. Okay, so half-life was the thing that we learned on Thursday and Friday, actually nothing new on Friday. You also have to know the nuclear equations and the different kinds of energy given off, alpha and beta particles and gamma waves. Okay, and then it was half-life. So today, very briefly, it's artificial transmutation. Artificial transmutation is, let's see, different color here. What happens here is that we bombard the nucleus. I can hear Aiden laughing. So funny Aiden. Going, here it is. By bombarding the nucleus. And when that happens, it converts it into another element altogether. And what are used? Got to use some sort of high energy particles. For example, protons. We can use neutrons, but there's a question with that. And you'd think electrons might work, but they're not heavy enough. So I would use something like an alpha particle. I can do that. Okay? So particle accelerators are machines that produce beams of high energy particles. And let's look at this. Okay, this is a picture that I pulled off the internet of a particle accelerator in Batavia, Illinois. And the way it works is it's really kind of interesting. Essentially, let me just pull this up here. Essentially, there's a giant tube, and that big circle that you see is a tube that goes all the way around, more than a mile. So what happens here? We've got the source of whatever the particle is. And if you notice here, we've got positive changing to negative, and vice versa. Now, the way they do that is by changing the magnetic polarity here. So they've got giant magnets that go all the way around the outside of this tube. And when they turn this oscillation on, when it goes from positive to negative, when it's positive, it can pull a negative, and when it's negative, it will push the negative. So it doesn't matter which type of particle that you use, positive or negative, but it has to be charged. So when we go back to this, and it asks, neutrons alone cannot be accelerated, now you should have the idea as to why. Because if you're neutral, you're not going to be affected by a positive or a negative charge. So what they have to do is attach the neutron to something else and then later on strip it off. Okay? So if I've got a positive particle, it's going to be attracted now and then reflected. Attracted and then pushed on, because it wants to be attracted by the negative And then once the positive shows up, it wants to move away from the positive. So you can see that these two will always be opposite, and I don't know what the span of space is, but it's going to do that, and as time goes on, once they start it, they will make this go faster and faster and faster, this change, and as time goes on, it accelerates and goes faster and faster. So eventually you get a particle that is moving at incredible speeds, almost to the extent of the speed of light, and then they have something in front of it. They divert it, and then they have something in front of it, another atom, and then that particle hits it with such speed that it explodes. Okay? That's essentially what it is. Now, this is not natural. This is what we call artificial. So in artificial transmutation, you're going to be able to tell the difference here because there will be more than one reactant. And this smaller part, of course, is the particle that is going to be accelerated. So in this case, we're bombarding aluminum with an alpha particle. When that happens, it destroys the aluminum and turns it into a phosphorus. And what happens? A neutron comes off. Okay, so this is artificial, and it's the same idea though to figure it out. You just take these two, have to add up to these two. There's really no difference except that we have another reactant here. So if I take a neutron, put it through a particle accelerator, you'd have to attach it to something. We're not going to go into the details of that. That neutron going at very high speeds is going to bombard the copper. So what happens here? It's going to break the copper down into cobalt. So this is 60. Over here I've got 63 plus 1 is 4. So this has to be 4 over here. Here's 29, and that's 0, so my total over here has to be 29. Right here it's 27, so I need a 2 here. So by now, hopefully you can tell that that's a helium atom, and just to remind you, that's an alpha particle. Okay? That's how you do it. It's pretty straightforward. There's only introduction of one new thing there, that's all. And this is the sheet that I want you to do. I want you to do the odds here. Whoops, didn't want that to happen. I want you to do the odds and the first two on the half-life, just to remind yourself of how that works. Okay? So odds on this and half-life sheet 1 and 2. Okay? I will plan on having a Zoom, Google Meets tomorrow, probably at 2 o'clock again. That seems to be a good time. All right? Email me with any questions.